reading if you want to do, we have to select the address where you are trying to read. Here also addressability is important. You are going to read 3 bits together, okay, depending on whatever is your addressability. So because there are 2 addresses, the size of the address is going to be 1 bit. So let us see how this architecture is going to look like. You have these are your D flip-flops, which is going to store your data. Now you are going to issue this address, right? ADDR is basically your address, and this address is going to be only of 1 bit. So either it will be 0 or it will be 1. Okay. So if it is 0, as you can see, the first line is going to be activated. The first row is going to be activated. So if address is 0, this is going to be activated because this will become 1, right? So all these AND gates that we are seeing here are going to be activated, okay? And what you are eventually getting, and then the other one is going to be 0, right? Because this is not, so that's why it was 1. This is going to be 0. So these things are going to be all 0. So there is no impact, right? So what you really obtain here is the output of the first row, right? The top row, right? If it is 0, we basically get the output of the top row. Here also the top row. And you can very easily understand that if address is equal to 1, then we are going to get the contents of the bottom row. If the address becomes 1, this is going to become 0 and this is going to become 1. In that case, we are going to get the bottom row, right? So this is going to be deactivated, okay? So green is the bottom row, okay? So this is how we read from the memory. This is the word line, right? And typically the thing that we are trying to do here, if you think carefully, is something that a decoder does, right? So in this case, it was only a single bit. A single bit was decoding from a top row and a bottom row. What if our address is of size 4? Your number of bits are going to be 2. So from 2, we want to look up from 4 rows, right? So this is basically a decoder. So the address is of size 2 bits. Total number of the address space will become 4. So 1 out of the 4 has to be chosen using these 2 bits, which is basically nothing but a decoder. So that is why it is called an address decoder. It is very important in all these memory systems. We have to look up memory using this address decoder. So you issue an address, the address decoder is going to tell you where in the memory should I go, okay? Which word or which row is going to be activated. That is done by the address decoder. The other thing that has to be done here is a multiplexer, because the outputs are coming from multiple D flip-flops, right? Although not all of them are activated, but the outputs are coming from multiple places. So we actually need a multiplexer to determine from where I want to read the output from, okay? So you have an address decoder and you need a multiplexer. Typically, this is the architecture of the memory system that we are talking about. Writing is also very similar. You have to have this write enable, right? Because earlier we were just simply issuing the address and we were able to read from it, right? But currently we are trying to write. So apart from just the address, we also want to have a write enable signal. This write enable signal is going to be also considered along with the address. So the address decoder has to select that particular row, as well as the fact that the write enable signal has to be high. If the write enable signal is low, then you cannot write, okay? So that is kind of important. So write enable signal along with the address is going to activate a particular row here, okay? Note that the right enable signal is commonly fed, right? If this signal is true, it is going to be true for all of them, right? So that has to do with the addressability. The bit, the number of bits that we are addressing here simultaneously is 3. So together, if we combine these two concepts, we are going to have both reading as well as writing to the memory array. Okay, so this could be a memory array, and you have 6 bits together. At one location, you are going to have 3 bits. So 3 bits plus 3 bits, same thing. We have write enable, and we are issuing a here in this particular case, we are issuing a 1-bit address, and you can make it bigger. So the last example that I was telling you was about this 2-bit addresses, the address space being 4, right? Here it is a 2-bit address. So there are 4 uniquely identifiable rows, right? Top row, second row, third row, fourth row. Okay, depending on the address, I am going to select one of these rows. So in this particular case, the number of bits that we have is 12. 3 bits, 3 bits, 3 bits, 3 bits. You are choosing one of these 3 bits. So if you see, the left hand side is basically your address decoder. It is nothing but it is generating all the different possible mean terms, right? For example, this is 1 1, right? This is 1 0, this is 0 1, and this is 0 0, right? Depending on the value of the address, one of these mean terms is going to be activated, and if write enable signal is on, that particular row is going to be allowed to be written to. Okay, this is something that we are using here. So we have address decoder. Address decoder will take care of the selection of a particular memory chunk or memory location, which is comprising of X number of bits, where X is the addressability, and while reading, right, we need a multiplexer where there are multiple inputs coming from the different flip-flops for that particular column. Let's say this is the D2 column. We are reading from that particular address, right? So it is going to come to all of the outputs are going to come to this multiplexer, and then we are going to read from that. Okay, so this is how you can actually increase the size of the memory by the same concept. You can always think that if you have 2 bits, from that you can have 3 bits. In that case, you are going to have 3x8 decoder, address decoder. You can use the similarly you can use a larger memory. Okay, so next thing, right, is something called a shift register. Okay, so here I just taught that what is a basic memory element. The basic memory element to hold this data you can read and write, that was basically a register or collection of registers. Okay, the next thing that I'll also kind of touch upon is called a shift register. Okay, so what is a shift register? Shift register is nothing but the register that has the flexibility to shift the data left or right. Okay, so in the last few slides, we were talking about a register that is a collection of flip-flops, right? So suppose it is a 4-bit register. You have a D flip-flop 3, D flip-flop 2, D flip-flop 1, and D flip-flop 0. That was a register. Okay, and you can use a collection of these registers to build a memory block, memory array or memory block, and we saw how can you use an address decoder to select a particular register or select a particular memory element and write there or read from there. Okay, now it might be necessary for some computational tasks to shift the contents of the register. Okay, so that is basically called a shift register. So the flip-flop stores 1 bit of information, as you know. When a set of n flip-flops is used to store n bits of information, such n bit number, we refer to these flip-flops as a register. A common clock is used for each flip-flop in the register. So whenever, as I told you earlier also, if you are having a 3-bit register or 4-bit register, those bits are going to be updated simultaneously. Okay, so now coming to the shift part, the bit that is content by the, let's say, a particular register in the next clock pulse is going to be shifted either to the right hand side or to the left hand side. Okay, so I can give you an example. Let's say my initial, maybe I'll do it here so that there's not much of noise. If we first understand this and then I'll go to the implementation. So suppose the register content is this. The register content, I have something, let's say 0101. I have a 4-bit register. Okay, so now if I shift the content to the right hand side, every flip-flop's content is going to be copied to the if I am planning to shift to the right hand side, to the right hand flip-flop, right? So if it is doing a right shift, if I am trying to do a right shift, after the application of the clock pulse, it is going to shift to the one place on the right. So this one is going to be shifted, right? So this one is going to become 0, right? This one is going to be shifted here, right? So this is going to become 1. This 0 is going to be shifted here. So this will become 0. And here, unless and until it is defined, right, what exactly is going to come here, one option is that the last bit 1 that was being talked about here can directly go back, right? But that depends, right? That depends on, there is no specific convention what has to be done. Typically that is called a rotation. Here we are just talking about a shifting, so we will assume that by default from the left hand side it is going to be replaced by 0 only. Okay, so if you do, so right shift 1, if you do one more right shift, let's say right shift 2, which is the next clock pulse, again one more 0 will come in, one more 0 will come in, so and this 0 will go out, right? So it is going to be something like this. Okay, if you do one more clock pulse, it will become 0 0 0 0. This is a right shift operation. Similarly, if you do a left shift, what will be the contents of the register? I will use another ring to indicate the left shift. This 1 is going to be copied here, this 0 is going to be copied here, this 1 is going to be copied here, and as convention this could be replaced by 0, as this was replaced by 0 also, right? So this will become 1 0 1 0. Okay, so this is after one right shift, one left shift. Okay, if you do one more left shift, this 1 is going to go out and it will become 0 1 0 0 and so on. Okay, so there are many interesting applications of this shifting, why these shifts are required. One common application in our computer's processor is that it's a very easy way to divide or multiply by 2. Okay, so any power of 2, suppose you want to multiply a number by 16, right, which is nothing but 2 to the power 4, this is equivalent to making 4 times left shifts, 4 left shifts. If you want to divide a number by 8, which is 2 to the power 3, this is equivalent to doing 3 right shifts. You can test it out. This number that I have assumed here is 5, right? 0 1 0 1 0 1 0 1. This is 5. If I do a right shift, what is 5 divided by 2? 5 divided by 2 in integer arithmetic is going to be 2. There is nothing called 2.5 here. It will be 2, right? So it has become 2. What is 2 divided by 2? 2 divided by 2 is 1, right? So it has become 1. Similarly, if I do a left shift, 5 multiplied by 2 is 10. What is this value? 1010. 10 10 1010 is how much? This is 10. Okay, so if I do one more left shift, we cannot capture 20 using this many bits, but if we had, let's say if it was a 5-bit register, right, instead of having 4 bits, then literally we could have seen that. We can try seeing what happens. So this will become 1 0 1 0, and then a 0 is going to be inserted. You can try seeing what this value is. This value is 1 0 0 0 0. So this is 16 plus 4, so it will be 20. Okay, so 5 multiply by 2, so this was divide by 2, divide by 2. This is multiply by 2, multiply by 2, right? 2 times I have done. So 5 into 2 to the power 2. Okay, so this is very nice way to very easily multiply or divide, because multiplication and division, particularly if you want to do even integer multiplication, these are sometimes require huge circuits, right, and they have delays. And floating point multiplication and division are more it requires more sophisticated hardware. Okay, so with a very simple ALU, they might not have support for doing floating point computation or floating point multiplication particularly, right? And if we want to, in my algorithm, if I do not want to involve the multiplication hardware, I will always try using a shift on my own, so that I want to multiply with a power of 2. This could be very specifically using the shift feature, and just in one clock I would be able to do this shifting, right? So this is a very major application of using shift register in your programs where you want to do a multiply or divide by 2. There are many other applications. For example, this shift registers would also be used for inter-device communication, right? So let's say you have one device. Say this is device 1, and you have another device, device 2, right? Device 1 could be a sensor device, right? And device 2 could be some kind of a processor, right? So it could be an IoT processor or something. It's a temperature sensor sending data to the processor, right? So what might happen is that you have a register here, shift register, and you have a shift register here, right? And they have a common clock. Suppose they have a common clock. So with every clock pulse, what will happen is that device 1 is going to write shift, and device 2 is also going to write shift, and this particular linkage exists. Okay, so suppose you have this 4 bits here and 4 bits here. You have, let's say, A, B, C, and D. So with the first clock pulse, what will happen is that this is going to be cleared off. This will be A, B, and C. D will come here. After the next clock pulse, what will happen is A, B, and this will become C, D, blank, blank, right? After 4 clock pulses, as you can see, this A, B, C, D is going to be transferred from the sensor device to the processor. A very nice way to communicate from one device to other device. And actually there is a protocol which is based on this concept, not exactly what I told you, but this is based on this bidirectional sort of register. It can either do from the processor to the sensor or from the sensor to the processor. Both ways is possible, right? And there is something called an SPI protocol, which is a very common protocol in IoT systems, embedded systems, and so on. They do use this kind of a concept, right? So shift register, the point is that shift register has a lot of important applications. Rather than just telling that the bit is moving to the right hand side or left hand side, you should also understand where exactly this kind of things might find great applications. That was the reason I touched upon these 2 use cases, right? So as I told you, let us look at how this shift register is going to be implemented, right? You have already seen these kind of examples where we looked at, let's say, Johnson counter or ring counter particularly, right? What was this ring counter doing? The ring counter if you remember, if you go back to the slides on ring counter, you'll actually see that 1 is being shifted over the clock pulses, right? So if you see a ring counter, that's why we mentioned the ring counter, the last stage in the shift register, right? So the ring counter simply forwards this value to the right hand side. Next clock pulse, it is going to forward this value here. Next clock pulse, it is going to be here. But whatever is the content is going to be shifted to the right hand side. It is in this ring counter example, we were specifically restricting ourselves to only one bit high at a time. The rest of the bits are 0, but that is not necessarily the case. Okay, whatever the data is there, it's going to be shifted to the right, and that is a shift register. Ring counter is a specific version of the shift register. Okay, so if you look at the circuit also, as you can see, whatever is the data is going to be directly fed to the next stage. Whatever is the data is fed to the next stage. Whatever is the data is fed to the next stage, right? And this one might not be necessary because I do not have to send out from this part back to the previous one, which is going to be resulting in not losing the bits, right? So typically that kind of a shift operation is often called a rotation, rotate. So you shift, but the right hand side, most significant right hand side is going to go to the least significant place, or vice versa, based on whether it's a right shift or left shift. They will call it a right rotate or a left rotate. So these are the things that we have kind of already discussed about flip-flops and why level sensitive latches are not suitable and so on. So this is like kind of an old discussion. We don't want to discuss about that right now. You already know that if it is level sensitive, this shifts are going to take some amount of time, right? So there might be some amount of ambiguity, or because of the propagation through the different latches, right? Because it is going to take some time, right? So this is going to be copied here, this is going to be copied here, this is going to be copied here, and proportional to the length or the number of bits that we are storing in the register, definitely the amount of time the latch is high, it will be depending on that. Rather than that, we implement that as a flip-flop, which is an edge triggered device, and with that particular edge trigger, all the D flip-flops are simultaneously going to copy the content from the left hand side to the right hand side. So in that way, you can be rest assured that there is no such ambiguity or a problem because of that would have happened in case of a level triggered latch, right? So definitely we use flip-flops in the register. So this is how the shift register is going to look like. Because the data is coming in, right, and being shifted, that is one kind of an application where I keep on pumping serial data to the shift register. At a certain point of time, the shift register acts as a window, right, window of the serial bits that are coming in, okay, and then here the data is basically going out. So the window is of size 4 bits, and at every clock pulse I am reading the serial input data bit and progressing that bit to the right hand side. So in that way, these bits are propagating and ultimately it is exiting. That is one way of using the shift register. So as an example, I can show you that this is going to be, let's say, your window, right? Some window, a temporary window where you are actually seeing the bits that are coming in. So initially the window is 0, 0, 0, 0. Next time at t is equal to 1, the input at t equal to 0 was 1, right? So with the next clock pulse, this 1 is pushed here, right? So now the window becomes 1, 0, 0, 0. Next time 0 is pushed here, right? But this 1 is pushed here. Next time there is one more 1 that is coming in. So this is basically a serial input. Serial input is here. So I am basically putting 1, then actually 0 came, then 1 came, then 1 came, 1 came, like that, right? This is the latest. This is the latest. The latest in the sense this is the first one. I would say first. This came here and I have to put it in, and rather than that this is the newest. Okay, or this is the oldest. So they are coming like this. So here also, as you can see, at every clock pulse, these are getting shifted. One came here, and next clock pulse, one is going to come here. This one is going to go here. 0 is going to go here. 1 is going to go here. After this, this 1 is going to get lost, right? If you see this one, once I have this one comes here, fine. This one comes here, fine. This one comes here, fine. This 0 comes here, fine. But this is going to get lost. Okay. This is going through the output. Lost in the sense it is going to come out of the output. So Q4, in this particular case, it is this Q4 value. After that, Q4 is going to be updated by 0. At that time, this value is going to get lost. You can either store it somewhere, or up to you how you want to use it. Okay. So again, it is going to continue same way. This is going out of the system. Similarly, this is a sample sequence. Okay. So after this, it's going, and then it continues, right? So as you can see, the shift register in this particular case is like a buffer, where you can see what is the content right now, the last 4 content. For the serial input, what is the last 4 inputs that had come in, right? And that will be temporarily stored in the shift register. This is one mode of operation using serial data. The other one is something called a parallel access shift register, that is also useful, where I don't want to load the data into the shift register using a serial input. Rather than that, I want to apply data parallelly to all the shift registers simultaneously, right? So here you want to put the data, right? So this is my data, the data 3, this is my data 2, this is my data 1, and this is my data 0. I want to load the data simultaneously. Suppose I have a 4-bit register, I want to load the register using a 4-bit number in parallel, right? All the data 0 to data 3 are simultaneously issued. It's not that a parallelly a serial input is being done like this, one after the other, right? So in this particular case, if I want to load the shift register with a 4-bit number, let's say a 4-bit number, this will take 4 clock cycles, right? But if you are using a parallel access register, this is only going to require 1 cycle, because in the next cycle all the D flip-flops are going to be loaded. Okay, so here you can ignore this multiplexer for now, but I'll explain what exactly is going on. So in this particular system, we have a facility of both serial as well as parallel. So if it is serial, the data is going to be pushed from the left hand side and it is going to propagate and so on, right? And this is chosen, the multiplexer is chosen whether you want to do a load or a shift, right? If you want to use, let's say, load equal to 1, then that is definitely not shift, so that is becoming shift bar. If load is equal to 0, that means that I want to use it as a shift register. I mean, not a parallel load, but a serial input is going to be entertained. So depending on whether it is value is 0 or 1, either I will select the serial input or I will try to select the data input that I am giving simultaneously. So if it is load is on, if it is load is selected, then my parallel data, they are all going to be selected, because I will select this particular input of the multiplexer. Then with just a single clock pulse, this is going to be loaded with D3, this is going to be loaded with D2, D1 and D0. Okay, so this is an implementation where I can have both a serial input facility where I can put 1 bit by 1 bit, and with a given clock it is going to populate the registers. The other option is that I can also do a parallel load. So parallel load is going to take all the different inputs and populate the individual registers with a single clock pulse, and you can choose in between them using a multiplexer as shown. Okay, so this is one thing. The other one that I am not going to discuss in this particular slide is this is a shift right. You can also have a shift left. Okay, instead of feeding from a given flip flop to the next right hand side flip flop, because right hand left hand is basically our notation, right? While you build the hardware, this it depends on where you place, right? How you connect. Let's say if you want to connect or propagate the value of a particular flip flop to the so-called left hand side flip flop, it basically becomes a left shift register. Okay, so left shift or right shift, right shift is useful for division kind of purposes, whereas left shift will be used for multiplication, right? Multiplication by 2, and right shift will be division by 2, right? One quick example that comes to my mind where you need to use divide by 2 in your code is something like a binary search, right? In binary search, given the length of the array or length of the memory segment that we want to search, we want to go to the middle of that, right? To go to the middle of that, we need to calculate what is the middle index, right? That is a classical example where I want to do a divide by 2 operation. And that if you want to implement that kind of a thing in hardware, or even want to write a software program which is going to be very, very efficient, shift registers is the way to go, right? Internally, when you write an assembly level program, or if you write a high level program that is going to be converted to an assembly level program, most likely the assembly level program is going to be resulting in a shift operation to the right, because that is a very efficient way to do a division by 2. Okay, so we have looked into the construct of a register using D flip flops. Then we looked into a memory block, which is nothing but a collection of registers, and at the same time you also have a address decoder to know which particular location is being queried. It could be either for writing or reading. And then you also have a multiplexer coming from individual flip flops, and you can give an output for a particular bit position. Okay, so after looking at the concept of building memory blocks or memory arrays using this individual bits or individual registers, we looked into this concept of shift register. As I told you, it has a great amount of importance in the processors, ALU and so on. Shift is a very important application, has many different applications, and we looked into how we have these two versions of the shift register. One was using a serial input, and with every clock pulse the input propagates to the right hand side if it is a right shift register, or to the left hand side if it is a left shift register. But with every clock pulse it is only going to propagate only one location, to the right or left, right? The other variation, which is also importantly used, particularly in places like in the processor's arithmetic logical unit, or inside the processor, right? Not really in the ALU, but inside the processor, there are these registers. They might have to do a shift operation, or often we want to load the data in the register and then do a shift operation, right? So for loading the data, we want to typically load all the data together, right? Maybe I have one register, and from one register I want to copy the data to another register, right? So that is going to be a case of parallel input, because the output of the first register are going to be parallelly fed to the output of the other, to the input of the other register, right? So this might go to another register's input. So this together, this can be input to another register, and that is something that always happens inside a processor. You always have inter-register transfer. So from a particular register, you want to transfer the content to another register and move them around, right? So most of the task inside the processor deals actually with the movement of the data inside the register to register, right? Around, bouncing it around. Okay. So I will stop here. So this is about the counters, registers, and most of the sequential circuit designs are completed. We will try to now focus our attention on using the tools that we have learned till now in order to design a processor system, right? In the computer system is going to contain a processor, and we will try to look at the high level details of how a processor could be built. Okay. And these concepts that we have covered till now is going to be useful.